Hello everyone and welcome to today's webinar, Aqueous Battery Chemistry, Considerations from a Reactions Perspective. I'm Shannon Reed, the Director of Community Engagement for the Electrochemical Society, and this is the second webinar in a series organized by the ECS Pacific Northwest section. Before we get started, I would like to go over a few items so you know how to participate in today's webinar. Please make sure that your microphone is always on mute. This will alleviate any feedback or interruptions from the audience during the presentation. You will have the opportunity to submit text questions to the presenters by typing your questions into the chat section of GoToMeeting. You may send in your questions at any time during the presentation. We will collect the questions and do our best to respond to them during the Q&A session after the presentation with time permitting. If we run out of time for the Q&A, we may post an ECS blog with the answers to the most asked questions. Again, this is the second webinar in a quarterly series offered by the ECS Pacific Northwest section. The section provides opportunities for scientists and engineers from Washington State, Oregon, and Iowa to connect with researchers and participate in various events. Please reach out to customer service at electrochem.org to join a section or share your interest in chartering a section in your region. As a section, the Pacific Northwest group is organizing at least 2 events per year with quarterly seminars that are open to everyone and monthly seminars for the Pacific Northwest section, and an industry day where attendees can look for jobs in electrochemistry and build their own network with industry. The current slide shows the upcoming events organized by the section. This effort promotes extensive interaction and collaboration among universities, industry companies, and national labs. It also increases student and researcher interest and involvement with the section. ECS is also helping the Pacific Northwest section to establish an electrochemistry research award and student award to recognize scientists in our 3 states who made outstanding contributions to the field of electrochemistry. More details regarding how to apply for those awards will be announced soon. Now, I'd like to introduce the webinar speaker for today, Professor David G. He's an associate professor of chemistry at Oregon State University. His research interests pertain to the design principles of materials chemistry for electrochemical energy storage. He is a 2019 and 2020 highly cited researcher of the Web of Science group. He received the 2016 NSF Career Award and is currently an associate editor of Carbon Energy, a Wiley journal. He obtained his PhD in materials chemistry from the University of Waterloo in Canada in 2009. And then during 2010 to 2012, he was an NSERC postdoctoral fellow at the University of California, Santa Barbara. In today's webinar, Professor G will cover basic considerations in design storage battery chemistries, different types of batteries, including rocking chair batteries, dual ion batteries, and reverse dual ion batteries, recent conceptual advances on storage batteries that employ non-metal charge carriers, such as proton, ammonium, halides, and superhalides. Again, we welcome your questions. Please send them in at any time during the webinar using the chat feature. Professor G will try to answer as many questions as possible at the end of the presentation. Now, I'll hand the webinar over to our speaker, Professor David G.
So, well, we have been working on aqueous batteries for the last 4 or 5 years, and we touched on several different charge carriers, and we gained some understanding. So today, hopefully, I will do some okay job to share that with you. Okay. So, in terms of the big picture of battery studies, before I zoom in, I hope to give you some information about that. So for power batteries, I'm going to introduce what power batteries are. We need to get rid of cobalt, nickel, and potentially lithium. It's not going to be easy. That's probably for future topics. And capacitor-like batteries, we're going to touch on that quite a lot today. And low-cost storage batteries, again, what storage batteries are, I'm going to talk about that. So just give you the clue for storage, the size of the market and the impact, potential impact. We are here 2021. You see that bar is really small, and that's the entire installation of the global storage, including pumped hydro and everything, batteries, compressed air. And we are looking at, this is by Bloomberg, we are looking at by 2040, and this is the scale of increase. So if you think about a market, the job opportunities, and for academia to contribute, it's going to be a very rich field for the next 20 years. So what are storage batteries and power batteries? The difference is really storage batteries are for energy storage. We don't really pay too much attention to energy density, but it is going to be really sensitive to cost and a cycle life, because you don't want to actually do anything to it for decades, right? If you bury the storage facility underground. But for power batteries, right now, power batteries, the only option is lithium ion. People are looking at lithium metal, and lithium sulfur, lithium air, and those high energy batteries. And for transportation, it's going to be more sensitive to the weight, to the volume. So the density, you can call it, specific energy for the mass, unit mass, and energy density for the volume. So this is basically the whole picture of batteries we are studying, actually probably from the entire field. Of course, there are some other batteries for microchips. So in terms of the cost, we just talked about the cost of storage batteries. The cost we look at is not how much you pay initially, the capital cost. It's actually the combination of everything. The capital cost you pay initially, the maintenance cost. If you hire a technician to service this facility, you're going to pay for it, right? And also the cost of electricity. It's about the timing when we purchase the electricity to store, and it's going to be divided by the entire energy stored over the lifetime of the device. It's not just for the first several cycles, for as many cycles as possible. So this total amount of energy can be expanded to this product cycle number. Of course, we want to have that maximized, specific energy efficiency, and the depths of discharge. If you can only use 10% of your storage, it's not going to be so helpful, because you actually hold 90% of the device not serving for you. And another one is the liability. Whether your storage solution is absolutely safe. We need to have some infallible solutions for the storage, right? So it's not affordable really to have any disasters out of it. And we have seen some of that recently for lithium ion. So when we think about exploring different chemistry solutions for storage, it's not something we can just zoom in and get focused on lithium ion or a specific charge carrier. I have this question: do the field need a conceptual framework to really actually pass the entire field into different small topics, but they are going to be in the same framework? And it matters actually the parallax, from which angle you take a look at the problem. So I want to actually here start talking about the conventional, I would call it conventional paradigm, which is pretty much material science, I would say. So we have a certain actually choices of electrolyte we can use for lithium-ion batteries. We use ethylene carbonate, diethylene carbonate, and we use the same electrolyte for sodium-ion batteries. We use that for potassium-ion batteries, and we explore different electromaterials. So that is one dimension. And we typically use lithium ions and sodium ions for our studies. And when we say we discovered a new electromaterial, we typically, talking about a default charge carrier being lithium ion or sodium ion. And also, the chemical bonding between the charge carrier and the electrode is assumed to be purely ionic, right? So now, if we move beyond lithium and sodium, we have other options. I'm going to introduce that later. And if you have different charge carriers, you're going to find that, well, sometimes the ionicity dominates, but sometimes covalency also comes in to play a role, right? And in the end, how your battery works, how the migration, the diffusion of ions will compensate the charge neutrality, will also play a huge role in terms of the energy density and the operation of the devices. So this is actually some kind of journey I want to share with you. This is by no means, including every possible, trials in the field in terms of charge carriers, but we did actually start from lithium, and moving on, alkaline metal column, and then the field started to look at proton and ammonium. Iron battery, actually, that was like more than a centuries old, started by the Edison company. And magnesium, aluminum, you have heard a lot of that recently, zinc. And recently we started using copper 2+ as the charge carrier. I'm going to share some interesting result there. Copper, of course, started in 1958 from a patent, initially from I think from a French company, an oxygen, bromide, bromine, iodide, chloride, all these hydrogen ions. Now we have seen a momentum in a dual ion battery or anion rocking chair battery. So all these charge carriers, they're going to have different flavors of chemical bonding with the electrode structure, right? So, well, I'm going to just talk about it from two perspectives. One is from the thermodynamic point of view, and then I'm going to cover the kinetics. I will give you some examples. So starting from carbon materials, we have been working on carbon materials from 2012 to 2017 intensively for a few years, and we have learned some lessons there. It's quite interesting. For example, if you use graphene, you want to store sodium ions in graphite or on the surface of graphene, it's not going to work. Why? Because the binding energy between sodium and carbon, it's not going to work out. So basically, sodium ions or sodium atom, they like themselves better than binding with carbon. But if you actually have defects, for example, monovacancies, divacancies, even you have curvatures, even you have a creased or rippled structure of graphene, it's going to help you. It's going to avail some kind of binding between sodium ions. And we have some studies on a mechanism for hard carbon in terms of storing sodium ions. And eventually, we derived some design principle for hard carbon, which is more defective expanded structure for hard carbon to have a bigger capacity for sodium ions. And size matters, but it's not always dominant. So if you think about graphite cannot store sodium ions, but graphite can store potassium ions. And potassium ions are way bigger than sodium ions. So it's all about the entire thermodynamics, the Gibbs free energy for the reaction between the metal and the carbon structure, right? It's a simple reaction. If that reaction, the Gibbs free energy is negative, you're going to have the intercalation. So another example is, this is actually well known for spin-out structure. If we have, say, half of the stoichiometry and even less than that, we're going to have lithium ions all together. They all together move from the octahedral voids to the tetrahedral voids. And you're going to have a more compact lithium residential environment. The lithium ions will bind with the structure more strongly. And I have read papers talking about certain covalency between lithium ion binding with the spin-out structure. And if you just pay attention to the difference of the voltage, is quite conspicuous. It's much higher. We cannot just use ionicity to explain such dramatic difference in terms of the voltage. Quite interesting. And recently, we used the same sulfur electrode. We actually tested the storage of different charge carriers, including copper. This is quite interesting. If you see, the potential is way bigger than lithium. It's higher than 1.5 volt for the same sulfur electrode. We use the same sulfur electrode, which is nano particles of sulfur infiltrated in the porous carbon. And you're going to have 1.5 volt higher. So sulfur need not to have this mediocre voltage. It can have a super nice voltage, which is relatively the same as lithium iron phosphate. And of course, also the capacity is high. But here we didn't count the mass of lithium ions or copper ions. So the polarization is very small. I'm going to explain that later. So if you look at just the mass, including everything, including the sulfur mass, including the copper ion charge carriers, lithium ion charge carriers, of course, copper is too heavy. It's 63.5. Lithium is 6.94, and the capacity for the entire electrode, copper is actually not that high, but because of the voltage, and this voltage gives you the quality of the capacity. The capacity are not created equal. Some capacity you have a better quality, like this case, like the copper case. In this case, the quality is poor, right? You need more cells in series to provide the same voltage. You probably just need one cell for this copper case. And if you calculate the entire energy density from this, if we assume lithium metal as the anode, copper is actually doing better than lithium ion, all right? So for the sulfur system, it's very interesting. And another point here is, because the strong binding between copper, cuprous copper and cupric copper with sulfur, there is no solubility of polysulfide whatsoever. It's all solid confusion, a solid conversion, but for lithium case, you're gonna have this metamorphosis of different phases, and some of the phase in between is just simply out of control. The polysulfide moving everywhere, creating a later plating mass of insulating lithium sulfide, right? Now, if you look at just the solid phase, the cupric sulfide and the cuprous sulfide is almost a conductor. It's better than semiconductor. So they can behave much better if you just shrink their particle size be submicron. But for lithium sulfide, you have to make it really nano-sized, right? Probably less than 5 nanometers. So this is something I want to just give you some qualitative impression that chemical bonding matters, and it really depends on two parties to work on their interactions together. It's not going to be just materials. It's not going to be just ion charge carriers. It will be the interactions of these two parties. So that's the conductivity of the copper sulfide. Now, in terms of the solubility, as I just said, these intermediate, there's only one intermediate, which is cupric sulfide, and then eventually gonna have cuprous sulfide as the final discharge product. So no polysulfide problem, and it's actually going to be very efficient for the entire system. And this is not just for copper. It's actually, as far as I know, and we know, it's probably applicable widely to transition metal ions. For example, this case for iron, and we have the ferrous iron, and it's also very reversible. And we don't have, we have fused metal, we have ferrous sulfide. We don't have polysulfide dissolution problem. Everything is solid. Okay, so this is something I hope to share. You can design your sulfur batteries, potentially considering the charge carriers of transition metals. Now let's talk about kinetics. So kinetics is really about, one parameter we look at is polarization. This is actually a paper from Professor Wu from Ohio State, and this is about oxygen batteries. I think they studied potassium oxygen battery, very interesting system, and they used different charge carriers to characterize the oxygen reduction reaction and oxygen evolution reaction. One is a discharge, the other one is charging process. And if you look at the polarization for lithium, this is something unbearable for industry. So the polarization is like over 1 volt. Think about energy efficiency, or you call it round trip efficiency, would be miserable. But if you look at potassium, it's much better. It's much better. And we know potassium is a relatively soft metal, soft metal ion in terms of polarizability. The hard soft acid base series, and the reduced species of oxygen is superoxide, right? Superoxide, O2 and a superscript minus. So that is quite a soft base. That's quite a soft base. Combining with soft acid, look at that, right? The polarization is much smaller. And if you go for even softer cation, tetrabutyl ammonium, right? And this is much bigger. The polarization is even smaller. I just want to highlight this interesting phenomenon from this interesting paper, that you choose different charge carriers, you have the same oxygen reduction and the same oxygen evolution, the entire kinetic behavior can be completely different. So this is something we just we studied. We used the same bilayered V2O5 structure as the electrode, and we tried to insert ammonium ions and potassium ions into the structure, and look at a CV, right? CV is completely different, especially when we say this A1C1 pair, this A1C1 pair is going to correspond to the same probably redox behavior of V2O5, but this A1C1 is vertically aligned, and you know, according to the book by Dr. Bard, we call that kinetic reversibility. It means the polarization is very small, and if you read the book, actually it talks about absorption of ions, absorption of redox species on the surface of the electrode, and that electrode, you know, in a book they use mercury and some other micro electrode, and here we don't have those surface to talk about. We have the lattices. We have the lattices, and these ions are actually inserted inside the lattices, right? So now, if you think about adsorption, well, we may have some flavors of covalency in terms of the bonding for ammonia with the V2O5 lattices, right? Potentially between the hydrogen of ammonium with oxygen of V2O5 in terms of some hydrogen bonding, right? So potassium, well, potassium doesn't have that luxury. Potassium is a single sphere, you know, very homogeneous ion. And if you use this equation, well-known equation, and you use the mu here is the scan rate in a CV, and B value. If the B value is 0.5, we call that diffusion controlled. You know, typically that's we say that's redox reactions, but you know, now the definition need to be better defined. B value, if it's 0.5, that's diffusion controlled. If it's 1, it's non-diffusion controlled. You know, in other words, in the timing, during the interval of our measurement for its behavior, the electrochemical behavior is faster than the time scale we gave in the instrument. So we call that capacitive. And for ammonium, it is just unity, just 1, right? And for potassium, it's doing pretty well. You know, it's 0.7, 0.8. It's not bad. We can still call this, you know, quasi-capacitive, but it's way slower than ammonia. Now, in terms of the chemical bonding, you know, we did a simple FTR measurement, and you can see that this is the initial V2O5 and the VO evaporations, and we look at these 3 peaks. And now, if you look at potassium, well, you have some shift. You have some red shift. That's it, just red shift, okay? And from that peak to this point. And now, if you look at ammonium, for 0.3, that is at the end of the discharge, the deepest SOC, the state of charge, you see this peak is split. That is split. It means actually the reaction or the interaction is not homogeneous, it's heterogeneous, right? So you have some kind of directional behavior in terms of their reactions. Whenever we have directional behavior, we call that covalency, right? For ionicity, it's actually radiating to all the directions. We don't have direction in terms of the interactions. And you can see that this is really due to the hydrogen bonding. The peaks are splitting, right? That's very interesting. So my collaborator, Professor Greeny, in UC Riverside, he helped the computation here, and this is the differences between ammonium and potassium. You can see that ammonium, you have these electron cloud, the distribution of them actually are more delocalized, shared, sort of shared by ammonium and oxygen atoms. And there is 17% of charge transfer from the oxygen of V2O5 to ammonium plus. Essentially, the ammonium ion is not a 1+ ion, a 1+ charge carrier inside the lattice, is 0.83 plus. So that is quite interesting. It means actually ammonium ion itself can store energy, can store charges, right? And if you look at potassium, it's just pure aniston. There's no sharing of electrons. So we call that just pure ionic bonding with no covalency. And we gave a name for this kind of pseudo-capacitance, covalent ionic pseudo-capacitance. So this is a nice cartoon prepared by my former student, Dr. Wu Chou-Sin. And you can see, and this actual name is coined by, this monkey bar walking was coined by my colleague, Dr. Greeny. And you can see that different from spherical ions migrating, you have ammonium, which is a tetrahedron. It's going to walk inside the lattice like a monkey bar walking, right? Well, because the directional interactions, because the hydrogen bonding between the hydrogen atoms of ammonium and oxygen of V2O5. So you're going to have the transference of this ion. It's not going to be sliding. It's going to rotate, right? It's going to rotate. And we need more competition to see whether rotate is really faster than sliding. All right. So we had a, an audacious, I'll say, conjecture. So this is actually by no means probably pure, something you can take for granted. But if you have certain flavors of Lewis donor acceptor characteristics for the bonding between the ion and electrodes, well, probably going to have some pseudo-capacitance, just based on the empirical observations of us, from Dr. Ian Wu's TDA interaction, to this ammonium, and later on we have the more hydrogen bonding versions of Prussian blue. All right, now let's talk about the interaction of ions as charge carriers with the lattice solvent of the host. This solvent by no means has to be water. It could be water, lattice water. It could be other solvent you put into the structure. Now, so let me introduce Gross's mechanism. So this mechanism, I talked to Dr. Matt Law when he visited OSU, and we talked about this mechanism. I said, okay, wow. So I thanked him for reminding me this mechanism. This is going to be great if we actually have water infiltrated in the lattice of crystal structures of electrodes. Potentially, we can have Gross's mechanism. Well, what is Gross's mechanism? So the normal mechanism for charge transfer in electrolyte, we call that vehicle mechanism. Basically, the ions are solvated, and the solvated ions will have to push through. Think about yourself moving through a crowd, right? Moving through a crowd is going to be sluggish, right? You're going to have a lot of energy barriers to overcome. Gross's mechanism is different. You have the proton coming in, it's going to knock on the door of this chain of water molecules, and you're going to have hydrogen bonding formed, and this hydrogen bonding formed, this covalent OH bond will break, and this is going to be a domino card effect. You're going to have this hydrogen released, forming hydrogen bonding with this oxygen, and so on and so forth. Eventually, this hydrogen will be stuck with this water, and this hydrogen will be released at the other end of the chain, right? That's the beauty of Gross's mechanism. You don't have to transfer your ions. It's diffusion free. You can just have a cooperative vibrations of different hydrogen bonding and covalent bonding. Then there you go. The ions will be transferred from the other end. Now, the premise of this transfer is you need to have a strong enough secondary bond. Hydrogen bond qualifies that, right? And we're going to briefly mention about the halogen bond. Halogen bond, like iodide. Iodide interacted with iodine. That is a strong secondary bond as well. And potentially you can convert these secondary bonds to be a primary covalent bond. That's what happens with hydrogen bonding. That is converted into a covalent OH bond. All right, so this was introduced by von Grosses in 1804. I think it was first published in Rome and then later translated to in French. This is the version we can now read. Right? It's fabulous. It's really a genius discovery. 2 centuries ago. Now we need water. We need water to conduct protons, but typically, metal oxide electrodes or phosphate or sulfide, or think about inorganic systems. You won't have that is water that rich to really form some kind of Venice city structure for transportation, right? So now we thought about one thing. Well, we probably need some reticular structure, right? Some reticular structure. Then we have the scaffold, and we can put some water, but we don't want to have really a fluffy material to begin with. So we thought about the earliest version of MOF, which is Prussian blue, right? Prussian blue. In this case, this Prussian blue, we have roughly one third of vacancies, of the iron cyanide. So now, when we have the vacancies, and those vacancies will be occupied by water molecules. One vacancy will be occupied by 6 water molecules. And eventually, if you omit all the other elements, right, just leave the water structure, you're going to have this nice contiguous structure of water. And by the way, we did some kind of painstaking effort to characterize the Prussian blue we had. We have done PDF based on neutron scattering. We have done synchrotron, with our collaborator in Argonne, Dr. Jun Lu, and Dr. York Neifeld in Oak Ridge for the PDF. So now Dr. Greeny computed the continuous structure of water. We found that 95% of water molecules are talking to each other, right? They are talking to each other by hydrogen bonding. That's great. So, this gives us the confidence that we probably will observe something that is really fast. So this is the Prussian blue, and from 1C, and we actually just select this range of cutoff potential, right? From this range. If you go even deeper, you're going to actually activate the copper 2+ reduction to copper 1+, which is really sluggish polaron. We don't want to actually wake that up. So now, if you just look at this iron 3/iron 2 polaron, it's really, really fast. From 1C to 100C, it's like it doesn't happen. From 1000C to 6000C, we only see ohmic overpotential, right? So we don't have concentration overpotential. We don't even have electrochemical overpotential. And if you actually look at this system, it really overclasses the other systems in terms of its behavior. And we have only one comparable behavior, which is actually the nickel oxo hydroxide film, but that is really thin and is pasted on some mesh, I believe, if I memorize that correctly. So this is really fast. As I just said, it's not something we have to diffuse ions through the structure. So it's really different from the existing mechanisms nicely laid out by our peers here, right? So, for example, the surface redox behavior and the intercalation pseudo-capacitance by Professor Dan in UCLA in a series of papers, and we don't have to rely on diffusion at all. So, we gave it a new name, Grosses pseudo-capacitance. So you need the ions to convert into primary bonding and so on and so forth, so that this can happen. Oh, the cycling, if you can have a nice rate capability, you can really cycle that. So I think this took us a few months to collect 0.7 million cycles, but you have to do it by a really fast rate. Now, talking about reversibility kinetically, So we can see protons, we still have that nice structure. So for capacitive materials, for capacitors, I don't think we have to look for rectangulars always. Rectangulars are good. They could be nice capacitors, but just having peaks vertically aligned, it's a very strong sign that your reactions is really fast. And for protons, we do have this. And for sodium and potassium and for ammonium, we don't have this luxury. They are very sluggish. And here the electron material is exactly the same. Now, this is some cartoon, again, made by my ex-student, Dr. Xiulie. And you can see that this proton is going to be released and migrating through some conduit of water molecules. All right, so you see, eventually this proton is going to be stuck there, and this proton will be released. Another proton is transferred, right, through the water chain. And this is actually by a simple relaxing process. Dr. Xiulie put the proton in some kind of uncomfortable, awkward, energetic sites, and then proton said, okay, well, this is not so comfortable, let me move. I think this really qualitatively supports the Gross's mechanism that if the energy is not the minimal, proton will move and proton will go through its conduction by Gross's mechanism. And so proton conduction is really fast. To say it's really fast, give us some kind of a look to another possibility. Why not studying its low temperature behavior, right? We know Arrhenius equation, and also the activation energy and the temperature. There are all kinds of correlations, and temperature is really important. And when the temperature is lower, you're gonna have sluggish reactions. Now, so we see proton works even at minus 88 degrees Celsius. Of course, in this case, we have to use a really concentrated phosphoric acid. That is something we really happily discovered, by Dr. Jiang, who has just graduated last September. If you have 62% of phosphoric acid, it doesn't freeze even at temperature above minus 85 degrees Celsius. So that is very useful. All right, so I think I probably finished my part for electrode ion chemical bonding. Now let's use some time for the last part, which is battery configurations. So in terms of battery configurations, we have to really talk about the cornerstone principle of charge neutrality. When we have batteries, actually, our battery electrodes inside the electrode structure, the mass or the active materials of the electrode is not charged. While the surface is charged, it's not electrostatically charged, but that's another story. So in order to have the electrodes stay neutral, but they are actually doing transactions of losing electrons or gaining electrons, how we can actually allow them to do their business with electron transferring, but still having the electrode neutral. We have to use ions to compensate that, right? So for anode, they lose electrons during discharge, and we need to either give them anions to compensate, or we take cations away, vice versa for cathode. So when we have these 4 boxes set up, we can make connections. This is well known. Lithium-ion batteries belongs to cation rocking chair, right? And we can have ion rocking chair. Recently, there are papers about fluoride batteries, chloride batteries, other batteries, and these are anion rocking chair. And dual-ion batteries initially introduced by this patent 3 decades ago, and you're going to have anode operating cation storage and a cathode operating on anion storage. So now let's talk about this dual-ion battery. So its operation looks like this. This is my previous student, Ish, and he's now in PNL. He's Linus Pauling fellow there, postdoc fellow there, and this is a cartoon made by him. So if you look at this is actually the discharge, and then going back charge, and going forward discharge. So it's like accordion. We saw, okay, why don't we give it a different name, accordion, right? Accordion sounds more vividly describing this mechanism. So, and we studied different systems. This is one example. We studied graphite, and this graphite typically will will actually cause, if you oxidize graphite in electrolyte, the electrolyte normally will decompose. That happens to organic electrolyte. If you use aqueous electrolyte, well, water will evolve into oxygen, right? And in this case, we studied a concentrated, you can call it deep eutectic solvent, or water in salt electrolyte, water in salt, which is quite popular, recently introduced by Dr. Xu and Dr. Wang. So for lithium systems, and we actually moved to zinc systems, and eventually here we have magnesium systems. And here we inserted magnesium chloride superhalide into the graphite structure, and we can have some nice charge discharge of graphite, although the Coulomb efficiency should be improved, can be improved hopefully, but we have some nice reversible iodine storage in graphite in aqueous electrolyte, right? We use this electrolyte that is effectively suppress the oxygen evolution and also chlorine evolution. Chlorine evolution will be quite severe if you have just a purely concentrated chloride electrolyte. And we collaborate with Dr. Fang at OSU, and you can see the evidence of the superhalide charge carrier. I don't have time to explain that in detail. Please read our paper if you're interested. Now, this is another example of Mn3O4. It's a crystal. It's a pretty solid, I would say compact structure, and we can have ammonium. We can have nitrate ion inserted. We have EQCM, which is electrochemical cross macrocrystal balance, macrobalance, evidence to show that we have nitrate in. All right, so this is another example. We have, again, we have chloride inserted into Mn3O4. And so far the evidence shows that if you have some zinc ions trapped in a first reduction, that's gonna help the following oxidation of the structure simultaneously having chloride ions inserted. And we have the EQCM evidence of that. And this is the iodide. This is the iodide. By the way, here we used concentrated zinc chloride electrolyte plus ammonium chloride electrolyte. I think I slowly gave you some clues of importance of electrolyte in terms of enabling different redox chemistries. And this is another example of electrolyte that enables the plating of iodine on a surface of a carbon fiber paper. And because we have this unique formula, right, of mixed zinc chloride plus potassium chloride, and once they are mixed, you're going to form a completely different speciation of the ions. You no longer have potassium iodide. You're going to have iodide arrested. The iodide will be arrested by the zinc complex ions. And then the concentration of free iodide will be minimized so that we can have the plating going on, right? So again, just to give you some clue on what we can do in terms of configuration of dual ion batteries. And here I'm only talking about anions, plating of anions, that's the best. If you can do that, please do it. And then if you can insert small ions like fluoride, chloride, that would be good because they're tiny, they're light, they're small, right? So these are interesting, I would say, principles. And iodine actually can be plated via this interesting Gross's mechanism, right? All right, so the last piece is called a reversible dual ion battery. Reversible dual ion battery, basically, we have the anode operating on anion storage and a cathode operating on cation storage. So I have one example, and we actually very luckily had a chance to define this different configuration. Right? By no means this is the first time anodes stores ions or cathode stores cations, but in terms of giving it a definition, I think that was the first time. So our example is for the anode side, we have ferrocene. We can have ferrocene, for the redox reactions, we can store the zinc chloride complex ions, the zincate. And on the anode, on the cathode, we can store zinc 2+. So far, I give you some flavors of dual ion batteries and a reverse dual ion batteries. In terms of reverse dual ion batteries or dual ion batteries, in terms of anion storage, there's an interesting phenomenon. If you actually increase the concentration of anions, the insertion potential will shift to a lower side. It will be lower, right? For reverse dual ion battery, that will be a boon. That will be a good thing to have. You're going to have the potential going lower, right? So that's going to increase the overall voltage of the battery. Right? That's something bear in mind. You know, if you have the potential lower, which is good actually even for the cathode to operate on anion storage, because you're going to minimize the chance of OER, you know, in this case, probably chlorine evolution and all the side parasitic reactions. All right, so I want to use probably 1 minute to highlight electrolyte. Electrolyte is the centrality of battery design. If you think about lithium-ion batteries can arrive today, it's because EC readily decomposes on the surface of graphite. It is the combination of a right electrode plus the right decomposition reactions of the electrolyte. You can have the SEI formation. Well, you know, we asked one question. SEI is great, kinetic control is great, but can we actually just manipulate or design the electrolyte formula to maximize the benefit of thermodynamic control? So this is something we have recently tried. We designed the electrolyte structure. We purposely avoided any fluoride in our electrolyte because we don't want actually to see SEI formed. We want to see how far we can go, how far we can push for pure thermodynamic control in terms of helping the zinc plating and a stripping efficiency. And we have actually pretty good results so far. And this is published in some recent publications. But in combination, in the future, if we really introduce some SEI on the surface, I think this problem will be settled, right? So plus, that's going to be thermodynamic plus kinetic. So kinetic control, SEI is great, right? But I think we probably arrive at a timing that we are probably done with understanding, but not probably that far. We still will study the thermodynamic control, particularly the water's behavior. Water is very intriguing. So, but now we'll probably consider kinetics control as well. With this, I want to just summarize what we have learned. So you have seen this dimensions of the the arrows initially. I want to highlight that in terms of electrodes, they're not something I think quite unique. They're just reactions. They're just reactant. I call it reactant A, and anionic charge carriers, reactant B. They are just reactant, right? They are just decoupled. They're separated, and you have to choose the right electrolyte as the media to allow them to react, right? And of course, we have to think about the chemical bonding, which is really about the nature of any chemical reactions. The configurations of devices, how you allow the ions to migrate to what directions, will be considered in terms of the design principles of batteries. But all by and large, this is really about a reaction. For chemists, I think we have this great opportunity. This is really golden for us, that we can design the battery chemistry holistically. And so I think by talking about that, I think I want to stop here and save some time for questions. And thank you so much for your attention. Oh, sorry, I want to actually thank my students and my collaborators and my funding agencies. Thank you so much.
David, thank you so much for that wonderful talk. It's great to see you and hear your voice and learn about all the exciting things going on. We have quite a few questions, mostly from me, posted into the chat. But I'd like to encourage folks, to post additional questions while we start here. And if people want to ask their questions live, I think, we're a large group, but we're not that big of a group. So I think if you want to ask your question live, that's fine too. So David, I'd like to ask one question, and then I'll go to Sung Pil's question here. And it's on the very last topic. This is something that we've been thinking about a little bit. So to what degree is the community convinced or not convinced that there's thermodynamic differences in the water and the decomposition? Is there any thermodynamic changes in water and salt electrolytes to the window, or is it all? You kind of implied that I think you implied at the end that there was some thermodynamic effect, maybe expanding the water window, or versus kinetic. And is this settled, the relative contributions of these, or is this still an open question in the literature? in your
That's a
understanding?
fantastic question. Yeah, thank you, Shannon. So I would say it's not settled. Not many people talking about it. There are some papers talk about it, but it's not probably widely accepted yet. But to me, I think my answer is yes. We work with Dr. Chung Fang at OSU, and his femtosecond Raman studies really shows the vibration of OH bond being vastly different for water molecules. And if you think about it, water actually can decompose at a lower temperature less readily, right? If you actually change its environment, for example, if water, if the OH bond is shorter, it's less likely it's going to be more robust, right? So the covalency will be strengthened, the overlapping of everything will be strengthened, will be less likely, less vulnerable for OER and HER. So
there's another thing you said is interesting, just to follow up on that, is you said temperature. And so I know that people often, water in these water and salt electrolytes is sort of ice-like water, right? And that's because apparently it's low entropy water. So that's right. That should also presumably perhaps change the delta G of reaction, right?
Right. Yeah.
Interesting. Okay. So sorry. Did you want to follow up there with anything?
Yeah, I totally agree with you. The entropy matters, and for competition, I think normally we don't think too much about entropy, but also in terms of competition, I think before Wuchou graduated, he had some interesting results in terms of water's environment. The water's environment is very different, and by not having hydrogen bonding helps stabilize water. That's quite interesting. Hydrogen bonding really weakens the OH bond of water. Yeah.
Okay, that's fascinating to think about. Let's move on to a few other questions. We have a couple questions from the audience having to do with the water and the mechanism in the sort of Grotus electrodes that you've been developing. So one of them is from Song Pil. He's a visiting professor from Korea, just showed up in Eugene actually a few weeks ago. And he's asking, is there a possibility of different structures within the Prussian blue of the water, basically? So is there a confined effect, and how does the confining of the water inside the Prussian blue affect the Grotus mechanism, and I think how we think about proton transfer in these systems?
Yeah, well, thank him for the question. It's a very nice question. So the reason we selected a highly diffective Prussian blue is that we want to give the chance for water to talk to each other. In terms of the crystal structure, if you have different, I would say, vacancies, you need to have the contiguous connection from one sphere of water in one void to another sphere of water in another void. They have to talk to each other, right? So the more vacancies you have, the better. The better. They have more freedom. You want to give water some freedom. If they rotate more easily, they're going to conduct protons faster. But you don't want to actually give the structure, too much water. It's going to lower the energy density. It's going to lower the capacity. So there are going to be some sweet spot you can hit, you can strike in terms of having the best optimized rate behavior, and also considering you don't lose too much capacity. Yeah. So for these particular porous structures, it's easier to control. I think the harder topics will be how to translate these kind of knowledge to some more compact structures. And that'll be something to study as well in the future.
So we have two other great questions that have come in. So one of them from Manikam from Murdoch University in Australia, has a question about how to think about conceptually the Grotus charging mechanism in these Prussian blues. Is it right to think about it as a combination of EDLC and redox behavior, or is it more purely Faradaic, or how do you think about that?
Yeah, that's a really interesting. I mean, this is something, I have been, as Shannon, we collaborated, right? We collaborated on this project about capacitive storage, and I have been thinking about what is capacitance, right? That is something, I think vaguely defined and people debating on it. So
I have a definition for you. Sometime we can talk. It's very, very physical.
Yeah, I'll be happy to learn that for sure. So, just going back to the student question, thank you for asking this question from Australia. I think this is, very late for you in the night. Thank you for staying up. So, in terms of EDRC, I don't think there's much, because the particle sizes we had for that material is, around 70 nanometers or 100 nanometers. So the external surface of this material is not that great, right? EDRC, we talk about external surface. The ions in the EDRC, the ions in the electrical double layer, typically they are solvated or partially solvated, right? So, to have partially solvated ions stored, we only talk about external surface. And our electro materials, this Prussian blue, it's not, really fluffy, it's still it's still nanomaterials. So EDRC is not going to be a big thing in its contribution. But going to whether it's ferritic or non-ferritic, it's certainly ferritic, because we have the iron, we have iron reduced from 3 plus 2 plus, during discharge, 2 to 3 during charge. It's certainly ferritic, but this is a diffusion-free ferritic. And that's that's actually why we think Gross's, this gentleman deserves his name in some pseudo-capacitance theory, right? Right. So it's fast. It's not conventional intercalation, insertion, or we call it surface reactions, surface redox reactions, defined by Conway in his book, right? It's different from that. So it is pure ferritic, but it just doesn't rely on diffusion if you allow it to be like that.
Yeah, there's no diffusion over, there's no transport over potential is very small, Let's see here. There's a few other great questions. We're gonna have to finish up soon. I'm not sure, Shannon Reed, the other Shannon at the Electrochemical Society, if we have a hard stop at 11 or if we can go on a little bit. But I'm gonna ask a couple more questions here. There's a question out of Oklahoma State from Oscar Capraz, assistant professor at Oklahoma State. He's asking about the copper sulfide battery and wondering about retention, so capacity retention, and what about cell volume changes as you move between the copper sulfide and compare that to polysulfides. Just a quick answer there.
Good question. So, let's talk about the volume change first. It's the cupric sulfide and the cupric sulfide. They're really dense compound. About 4 point something gram per cc. So although we add a huge amount of mass of copper ions into the sulfur mass, we only see less than, I would say, 1.7 times of the volume change. So you have 70% more volume from sulfur to cupric sulfide. 70%. Well, it's similar to sulfur with lithium. Think about that, right? Lithium is so light. So that's one thing. In terms of reversibility, we have some characterization, we have some cycling performance in that paper. It's really reversible. Why? Because we don't have polysulfide dissolution problem. When we actually taking care of that, we don't lose active mass to the electrolyte. Now, another attribute of this system is that cupric sulfide is really conductive. It's really conductive. Even you form some bigger particles, it's still pretty conductive. So conductivity is really the premise for electromaterials to really perform their reactions. If they don't have conductivity, they will not be able to convert back and forth, right? So we have a pretty good.
Yeah, I was going to ask. Sorry, for the copper electrode, copper sulfide system. One thing it seems like maybe an issue is, if I think about a lithium-ion battery, right? We typically have a pretty high lithium-ion concentration in the electrolyte, so you have low concentration overpotentials. You can build a set. So in a copper battery, apparently you would presumably have copper at the positive electrode and do something else at the negative electrode, right? Isn't that the right? And so then you'd need a high concentration of copper, but you'd only use it sort of at one electrode. I'm wondering, like, is that a problem? Like something like big, like copper, or basically any transition metal. One, can you get them in these high enough concentrations in non-aqueous solvents that are compatible with lithium-ion chemistry? Or are you thinking water and salt chemistry? Or how do you actually think about putting together a real battery, not just sort of a half reaction? And what would it be? Are there serious limitations to energy density if you use a transition metal, or or can we get around that?
That's a great question. Shannon, you hit right on the target. It is something we have been thinking for the last couple of years. I think the importance of this paper actually is pretty high. I think it's not just the current system we look at in a paper described. It has all kinds of possibilities. It really depends on the ingenuity of the researchers, how to utilize this system. So certainly there are a lot of things you can do. There are a lot of things I don't want to disclose on that because we're working on that now.
Right.
but this is quite fascinating. We're still very excited about the system, and we are working on it. And potentially this may not be just for copper. It could actually extend it to other ions as well. But it's interesting. But you have to really decouple the two electrodes, right? You cannot actually having copper ions hanging around near the anode because copper 2+ is oxidizing, right?
Okay, right, sure, of course. Okay, so let's see here. We have a few more questions. Prospero Pena has another question about the difference between capacitance or fast kinetic redox processes. I think I can answer that one. You've already answered that, David. We're really talking about fast redox, primarily redox processes. You have transition metal ion valency changes. It's just that the diffusion is so fast, it looks like a capacitive response in the sort of nomenclature and analysis that someone like Bruce Dunn would do, right? So if you do a scan rate dependence, you get this exponent of 1. That just means it's diffusion. There's no diffusion contribution to the overpotential you're measuring. So that's an easy one to answer based on what David already told us. Here's another one about water and salt electrolytes, and we're starting to lose lost about half of our audience. About half people are still here, so that's great. And then I think we'll take this as the last question, and then I think we'll wrap up with Shannon Reed, just so folks can get on with their day. He has a few comments at the end. So how do water and salt electrolytes act in concentrated electrolytes? And what's the idea of free water? How much free water is there? The other question: do they undergo hydrogen bond transfer in very concentrated electrolytes? So sort of maybe a little bit discussion about how you think about the concentrated, super concentrated systems and compared to free water, and what are the key differences there in sort of the fundamentals. You touched on this, but maybe a little bit of elaboration.
Yeah, well, also good question. So, water's behavior in water and salt electrolyte is something a no man's land. We have very rudimentary understanding on this topic. I mean, from probably the community of energy storage, and our friends in physical chemistry probably have studied these systems for decades, but they don't have probably the interesting ions used in their systems. So to us, but I would call this is something very promising. So I highly encourage our colleagues to think about and puzzling, especially water's behavior in these systems. And it really depends on its chemical environment, and it depends on the speciation of ions, both cations and anions, and their polymers, tremors, all kinds of species you can think of. And they do have a huge impact on the behavior of water. And to us, the behavior is electrochemical. It's oxygen, the redox reactions of water. So we do see the hope that you can suppress HER and OER to a large extent by tuning the chemical environment.
Okay, and actually I want to ask one more question, a really big picture question. It's from James Thode at Anton Par, and he asks, what is the most promising material system that you think right now to meet global energy demands in the next 10 years? And I think, well, I mean, lithium ion in the next 10 years is probably it, but not lithium ion. So what's the most promising system that's not lithium ion? It just a really quick, if I gave you $1 billion and you had to put it on some technology that was not lithium ion, what would you put it on?
Well, I think that's something I don't have the I think authority to define. If I could define that, I think I would be already super rich now. But but I think in terms of the field, I probably just use half a minute. We need to move beyond cobalt and nickel and potentially lithium for power batteries. We have to. Cobalt and nickel, they are not going to last forever, and lithium will not last forever. We cannot actually use them for the cars for obviously 100 years to go. For storage, aqueous, I'm still highly interested in aqueous systems. It's just so friendly to the environment and safe. And there's no conclusion now which system will win the market. I think we'll see, hopefully in the next 5 years, the whole market will tell you the answer.
Okay, wonderful. The market will always in the end tell us the answer, won't it? Okay, so let's now go back to Shannon Reed here, who will wrap up. Thank you so much, David, for the great discussion to follow your talk. Thank you for all the attendees, for all the wonderful questions. There's a few more questions for me, David, that I just typed in along the way, if you're curious of looking at those in the chat. So Shannon, take it away.
Thanks, Shannon. It's always great to have more than one Shannon on a call, right?
Very odd feeling, to be honest with you.
Yeah. Well, just to round out today's presentation, I had a couple of announcements or things that I would like to share with the attendees. We know that the webinar program is a great way for our community to engage, and that many of our members get started through the biennial meetings or section events. So, we always encourage the attendees to a meeting or attendees to the webinar to join the ECS community if they're not already members. We have membership options for well-established researchers, early career members, postdocs, and students. If you're already a member and you'd like to join the Pacific Northwest section, you can reach out to customer service at electrochem.org. Membership to the section is free, but you do have to have an ECS membership in good standing. You can also learn more about membership by visiting electrochem.org/join. Again, we want to give you a heads up to 3 other opportunities for you to participate in our meeting events this year. We are hosting the 239th ECS meeting with the 18th International Meeting on Chemical Sensors starting on May 30th to June 3rd. Registration will open next month in April. Pre-registration is required, but there is no fee to attend the meeting, and we are accepting late abstract submissions until May 14th. The second is the 17th International Symposium on Solid Oxide Fuel Cells, hosted by the High Temperature Energy Materials and Processes Division of ECS and the SOFC Society of Japan. We encourage you to register by June 21st. Registration will open in April. All the details are available on the ECS website at electrochem.org. And then we are still planning an in-person meeting for the fall biannual, which is the 240th ECS meeting to be held in Orlando, Florida from October 10th through the 14th. Abstract submission for the event is open, and the deadline for abstract submission is April 9th. ECS also hosts a bi-weekly webinar series. If you'd like to find out more or participate in other ECS webinars, you can visit electrochem.org/webinars to learn more and register. With that, I want to give a tremendous thank you to Professor Bocher for moderating the webinar and Professor David G for presenting. As a reminder, mark your calendars for the next ECS Pacific Northwest Section webinar, which is going to occur on April 8th and feature Daniel Schwartz from the University of Washington. Thank you everyone for joining us, and the webinar is now over.